Hello, welcome to the course on cloud computing. I am Sapna Rajvanshi from R.C. Patel Institute of Technology, Shirpur. Uh, it is important to understand the classical data center environment before discussing virtual data center and cloud. This module focuses on the key elements of classical data center: compute, storage, network, with focus on storage, networking, business continuity, and data center management. This module does not cover classical compute and network in detail based on the assumptions that audience is already familiar with them. The lesson covers application, DBMS, physical and logical elements of a compute system, different storage device options, RAID, that is RAID technology, and intelligent storage system. The core element of classical data center include compute, that is server, storage, network, application, and DBMS. An application is a computer program that provides the logic for computing operations. Application may use a DBMS, which uses operating system services to perform, store, or retrieve operation on storage devices. DBMS. DBMS provides a structured way to store data in logically organized tables that are interrelated. A DBMS optimizes the storage and retrieval of data. Compute. Compute is a physical computing machine, or we can say that server, that runs operating system, application, and database. Next is a storage. Storage refers to a device that stores data persistently for subsequent use. Network. Network is a data path that facilitates communication between clients and compute system, or between compute system and storage. These core elements are typically viewed and managed as separate entities, but all these elements must work together to address data processing requirements. Other elements of classical data center are power supplies and environmental controls, such as air conditioning and fire suppression. A data center infrastructure should meet following attributes to ensure that the data is accessible to its users effectively and efficiently all the time. So first attribute is availability. All data center elements should be designed to ensure accessibility. The inability of users to access data can have a significant negative impact on a business. Next attribute, performance. All the elements of the data center should provide optimal performance and service all processing requests at high speed. Next is scalability or flexibility. Data center operations should be able to allocate additional processing capabilities or storage space on demand without interrupting business operations. Business growth often requires deploying more servers, new applications, and additional databases. The infrastructure should be flexible enough to meet the changing business requirements. Data centers should be able to provide additional resources on demand without interrupting availability, or at the very least with minimal disruption. Next attribute is security or data integrity. It is important to establish policies, procedures, and proper integration of the data center elements to prevent unauthorized access to information. Data integrity ensures that data is unaltered. Any variation in data during its retrieval implies corruption, which may affect the operations of the organization. So manageability can be achieved through automation and reduction of manual intervention in common tasks. The additional resource requirement should be primarily be managed by reallocating or improving utilization of existing resources rather than by adding new resources. The cost of the data center management is one of the key concerns. Organizations are looking towards optimizing their IT expenditure on data center maintenance so that they can invest on innovation and new application deployment. This slide lists the commonly deployed application in a data center. An application provides an interface between the user and the host and among multiple hosts. So typical businesses application use databases that have a three-tiered architecture. The application user interface in front end tier, the computing logic or the application itself is the middle tier, and the underlying databases that organize the data is the back end tier. The application sends requests to the underlying operating system to perform read-write operations on the storage devices. Application can be layered on the database, which in turn uses OS services to perform read-write operations to storage devices. These read-write operations enable transaction between the front end and back end tiers. Application input-output characteristic is an important parameter and influence the overall performance of the underlying IT solutions. A database is a structured way to store data in logically organized tables that are interrelated. A database helps to optimize the storage and retrieval of data. Database management system is a collection of computer programs that control the creation, maintenance, and use of a database. The DBMS processes an application's request for data and instructs the operating system to access the appropriate data. The DBMS manages incoming data, organizes and facilitates the data to be modified or extracted by users or other programs. Some popular DBMS solutions are MySQL, Oracle, SQL Server, etc. So example, Examples of compute system are laptops, desktop, blade servers, complex cluster of servers, mainframes. Bladed server technology is commonly used to deploy systems in CDC, etc. Compute system may be a simple laptops, standalone servers, blade servers, mainframe computers, etc. They bring The blade server were developed in response to the growing need of a computing power that does not consume a large floor space. They bring down the cost and complexity in the data center. Blade servers consolidate power and system level functions into a single integrated chassis and enable the addition of server modules as hot plugged components. Blade server technology greatly increased server density, lower power and cooling cost, aids server expansion and simplifies data center management. Server. Server clustering is the method of grouping two or more servers, also known as nodes, and making them work together as a single system. This ensures that mission critical applications and resources are highly available. When the failure occurs on one cloud in a cluster, resources are redirected and the workload is reassigned to another node in the cluster. The cluster service is the software that connects the nodes in the cluster and provides a single system view to the clients that are using the cluster. So multiple servers or multiple nodes are brought together in a cluster to improve the availability and performance. So these nodes communicate with each other over a private network. Communication between the nodes of a cluster enables the cluster service to detect node failures and status changes and manage the cluster as a single entity. Heartbeat is a checkup mechanism arranged between two nodes through private network to see whether a node is up and running. The failover is initiated if the heartbeat is not functioning. In such cases, another node is cluster will take over the workload of the failed node. So server clustering offers several benefits besides high availability. It offers scalability by enabling clusters to expand non-destructively. It also provides load balancing by distributing the application load evenly among multiple servers within the cluster. Ease of management is another advantage of clustering because it allows non-destructive maintenance of server resources. The following are the logical components of a compute system. File system. A file is a collection of related records or data stored as a unit with a name. A file system is a hierarchical structure of files. File systems enables easy access to data files residing within a disk drive. A disk partition or logical volume. A file system needs compute-based logical structures and software routines that control access to files. It provides users with the functionality to create, modify, delete, and access files. Access to the files on the disk is controlled by the permissions given to the file and by the owner. These permissions are also maintained by the file system. Operating system. An operating system controls all aspects of computing environment. It works between the application and physical components of the compute system. One of the services it provides to application is data access. The operating system also monitors and responds to user actions and the environment. It organizes and controls hardware components and manages the allocation of hardware resources. It provides basic security for the access and uses of all managed resources. An operating system also performs basic storage management tasks while managing other underlying components such as file system, volume manager, and device drivers. Next is volume manager. Logical volume managers, that is LVMs, introduce a logical layer between the operating system and the physical storage. LVMs have the ability to define logical storage structures that can span multiple physical devices. The logical storage structures appear contiguous to the operating system and applications. The logical volume manager provides a set of operating system commands, library subroutines, and other tools that enables the creation and control of logical storage. Next is device drivers. Device driver is a special software that permits the operating system to interact with the specific device such as printer, mouse, or a hard drive. A device driver enables the operating system to recognize the device and to use a standard interface to access and control devices. Next is storage. Storage data created by individuals or businesses must be stored so that it is easily accessible for further processing. The devices designed for storing data are termed as storage devices or simply storage. The type of storage used varies based on the type of data and rate at which it is created and used. Devices such as memory in a cell phone or digital camera, DVDs, CD-ROMs, and disk drives in personal computers are examples of storage devices. A storage device uses magnetic, optic, or solid-state media. Disk tapes and diskettes use magnetic media while CD, DVDs uses optical media for storage. Removable flash memory or flash drives are examples of solid-state media. Next, the tapes are a popular storage option for backup purposes because of their relatively low cost and transportability. However, tape has its limitations. Data is stored on the tape linearly along the length of the tape. Search and retrieval of data is done sequentially, taking several seconds to access the data. On a tape drive, the read-write head touches the tape surface, which causes the tape to degrade or wear out after repeated use. Also, the overhead associated with managing tape media is significant. Optic disk storage is popular in small, single-user computing environment. Optical disks have a limited capacity and speed, which limits the use of optical media as a business storage solution. The capability to write once and read many is an advantage of optical disk storage. Optical disks, to some degree, guarantee that the content has not been altered. Hence, they can be used as a low-cost alternative for long-term storage of relatively small amounts of fixed content. Disk drives are the most popular storage medium for storing and accessing data for performance incentive online applications. A disk drive uses a rapidly moving arm to disk and write data across flat platter coated with magnetic particles. Data is transferred from a magnetic platter through the read-write head to the computer. Several platters are assembled together with the read-write head and controller, and this is referred to as a disk drive. Disks support rapid access to random data locations. This means that data can be written or retrieved quickly for a large number of simultaneous users or applications. In addition, disk drives provide a large storage capacity. Next is the solid state drives, that is SSDs, also referred as flash drives, are new generation drives that deliver ultra high performance required by mission critical applications. Flash drives use semiconductor-based solid-state memory, that is flash memory, to store and retrieve data. Drives are susceptible to failure due to mechanical wear and tear and other environmental factors. A disk drive failure could result in data loss. A disk drive has a projected life expectancy before it fails. So today data center house thousands of disk drives in their storage infrastructure. Greater the number of disk drives in a storage array, greater the probability of disk failures in the array. RAID technology was developed to mitigate this problem. The RAID is an enabling technology that leverages multiple disks as a part of a set. The technology also provides data protection against drive failures. In general, RAID implementation also improve storage system performance by serving IOs from multiple disks simultaneously. Storage systems with flash drives are also benefited in terms of protection and performance by implementing RAID. Stripping, mirroring, parity are RAID techniques that form the basis for defining various RAID levels. These techniques determine the data availability and performance of a RAID set. RAID controller helps implementing these RAID techniques. Stripping is a technique of spreading data across multiple drives in order to use the drives in parallel. All read-write heads work simultaneously. This allows more data to be processed in a shorter time. Consequently, performance increases when compared to retrieving data to or from one disk at a time. Mirroring is a technique where data is stored on two different disk drives, yielding two copies of data. In the event of one drive failure, the data is intact on the surviving drive, and the controller continues to service the compute system's data request from the serving disk of the mirror pair. Mirroring improves read performance because read requests are serviced by both disks. However, write performance deteriorates because each write request manifests as two writes on the disk drives. So mirroring is expensive because it involves duplication of data. The amount of storage capacity required is twice the amount of data being stored. Mirroring can be implemented with stripped RAID by mirroring entire strips of the disk set to strips on the other disk set. This is known as nested RAID. Parity is a method of protecting stripped data from disk failure without the cost of mirroring. An additional disk drive is added in the strip set to hold parity, a mathematical construct that allows recreation of missing data. Parity RAID is less expensive than mirroring because parity overhead is only a fraction of the total capacity. Parity information can be stored on separate dedicated disk drives or distributed across all the drives in a RAID set. Parity calculation is a bitwise XOR operation. Calculation of parity is a function of a RAID controller. If one of the disks fails in a RAID set, the value of its data is calculated by using the parity information and the data on the surviving disk. The value is calculated using XOR operation. However, there are some disadvantages of using parity. Parity information is generated from data on the data disk. As a result, parity is recalculated every time there is a change in data. So this recalculation takes time and affect the performance during write operation. Application performance and data availability requirements determine the RAID level selection. These RAID levels are defined on the basis of the RAID techniques implemented. Some RAID levels use one technique, whereas others use combination of techniques. Commonly used RAID levels are shown in the table. Business critical applications require high level of performance, availability, security, and scalability. A disk drive is a core element of a storage that governs the performance of any storage system. Some of the older disk array technologies could not overcome performance constraints due to the limitation of a disk and its mechanical components. RAID technology made an important contribution to enhance storage performance and reliability, but disk drives, even with a RAID implementation, could not meet performance requirements of today's applications. With advancement in technology, a new breed of storage solution known as an intelligent storage system has evolved. These intelligent storage systems are featured RAID array that provide highly optimized I/O processing capabilities. These storage systems are configured with a large amount of memory, that is called cache memory, and multiple I/O paths, and use sophisticated algorithms to meet the requirements of a performance sensitive applications. These arrays have an operating environment that intelligently and optimally handles the management, allocation, and utilization of storage resources. An intelligent storage system consists of four key components: front end, cache, back end, and physical disk. The figure on the slide illustrates these components and their interconnections. An I/O request received from the compute system at the front end is processed through cache and the back end to enable storage and retrieval of data from the physical disk. A read request can be serviced directly from cache if the requested data is not found in cache. An intelligent storage system, physical disks are logically grouped together to form a set called RAID set, on which a required RAID level is applied. The number of drives in a RAID set and the RAID level determine the availability, capacity, and performance of the RAID set. It is highly recommended that the RAID set can be created from the same types, speed, and capacity drives to ensure the maximum usable capacity, reliability, and consistent performance. For example, if drives of different capacities are mixed in a RAID set, then the capacity of the smallest drive will be used from each disk in the set to make up the RAID set's overall capacity. The remaining capacity of the larger drives will remain unused. Likewise, mixing higher revolutions per minute, that is RPM, drives with a lower RPM drives lower the overall RAID set performance. RAID sets usually have a large capacities because they combine the total capacity of individual drives in the set. Logical units are created from the RAID set by partitioning the available capacity into a smaller units. These units are then assigned to the compute system for their storage requirements. Logical units are spread across all the physical disks which belong to, to that set. Each logical unit created from the uh, RAID set is assigned a unique ID called logical unit number, that is LUNs. LUN hide the organization and composition of RAID set from the compute system. The diagram on the slide shows a RAID set consisting of 5 disks that have been sliced or partitioned into two LUNs, LUN0 and LUN1. These LUNs are then assigned to Compute System 1 and Compute System 2 for their storage requirements. It is also possible to control access of LUNs by a compute system. This is done with the help of LUN masking. LUN masking is a process that provides data access control by defining which LUNs a compute system can access. LUN masking function is implemented on the storage processor or controller. This ensures that volume access by server is controlled appropriately, preventing unauthorized or accidental use in a shared environment. This lesson covers the technologies used in compute to compute and compute to storage communication with focus on latter. It is it also covers details of DAS and FCSAN. The other storage networking technologies are covered in the next lesson.